So I'm going to talk about this topic. I know this title doesn't say anything. It's just light on the horizon. But, and you can see that this picture is sunlight coming from the horizon on Earth. But I want to convince you that this is also light on the horizon. Here we have a gold-plated parabolic mirror that shines several lasers to this photonic crystal fiber. So it's similar to what Carlos just showed. This is 7 millimeters length, so you can just blow it if you're not careful and breathe around this. And as you see, we put some red light, which is actually more than red. And when it goes out, you have some white light that includes some UV light. And this UV light, we call that it's an analog of Hawking radiation. And this is what that's why we have the horizon there, or an analog of the horizon. So usually there's even like kids experiment that show that light travels in a straight way, but it's not always the case. For example, when you have a nonlinear medium, in this case this is the mirage, right? You think that if you see this, you think that there is some water here, right? And why is it that? You have these kind of optical illusions, and the reason why we have these optical illusions is because we always assume that light travels straight. So I think that light is coming here, reflected, right? But that's not the case, right? This is a mirage, so when you get closer, it disappears. So in Mexico, we can see this usually in the asphalt, in the highways. So you see this kind of reflection, you see that there's a puddle there, but there's nothing when you get close. So actually, this is what happens. We think that light is coming from B prime because we extrapolate. We see light coming from that direction, so we think it was originated here in B prime, but it's just because the refractive index is changing due to temperature. Okay, so light bends, the non-uniform media bends light, and there is this other aspect that also bends light. So it's the same principle of this optical illusion. If we see light coming from here, then we think that this star will be in this position. This is what we call the apparent position of the star. But in reality, because of gravity, or general relativity, for the curvature of space-time, this is actually in a different position. So this is the real position, right? So it's again like the same kind of optical illusion. This is explained by Einstein equations. So it also, of course, space-time bends light. So we wonder if there's a way of joining them. So what do they have in common? And this example here is for invisibility, that I will not touch, but let's say it was one of the first uses of this theory. So we can have a medium in a flat spacetime. This is flat spacetime because the grid is squared, but it has a medium because there is some blue shade here. So this shade shows that the ring has a non-uniform refractive index, and then you can bend the light, right, such that it will not touch this inner part. And this just shows that it's flat spacetime and the medium is not empty. And you can do the same thing in vacuum, in a curved spacetime. Here we don't have any medium, we don't have any color, right, any refractive index, but we do have the curvature of spacetime, as you can see, because the grid is not straight. So the other thing is that I always like to tell my students to put the picture of what you're studying. So this is a picture of what I'm studying, this is a real picture. It is a black hole picture, you can see. So this is what we will be studying. We take a radiography of this, an X-ray scan of this, and then we can see. So this here is a solution. So the solution of the Einstein equation that I put before. This is just like the solution. So if you put this metric, it solves the Einstein equation. So we are only going to work on the solution. We will not have directly connection with the Einstein equation, but just with the solution of the Einstein equation, which means that what we will work is just a kinematic analog, not a dynamic full analog. So this, by the way, this Churchill, he solved the Einstein equation when he was in the front battle of World War I. He was working on this in his free time. So here, if you see this solution, it has two singularities. If r equals to 0, then you have a singularity. And also if r equals to rs. Rs is the Schwarzschild radius, which is proportional to the mass, basically. And you need to think about this. This solution, it's the solution for all symmetrically spherical masses. It's like in electromagnetism, in bachelor, when they teach us that you have a sphere and you can just think about it as a point particle, right? But the solution is only valid for a radius bigger than the sphere, right? So for example, this metric is also the metric for the sun, but it only is valid after the surface of the sun. So yeah, so the sun has also a Schwarzschild radius, but it's inside the mass. So if you think about like the sun, it's because you're applying the theory in a place that you shouldn't, right? For this solution, you consider that all the mass is in one point, but it really is not. Okay, so this is singularity, and what you can do is to change coordinates, and then you realize that the event horizon, or this r equal to rs, is not a real singularity, because you can just change the coordinates and it's no longer singular there. It's what it's called the event horizon, right? So what is this event horizon? We can think the space-time as a fluid. Yeah? So you can think like water is flowing, right, to some hole, and you imagine that there's some flow of the space-time that it goes faster every time, and this flow is so fast that in a certain point for a certain radius it surpasses the speed of light. In that case, then light cannot escape from this hole, right? This is what it's a black hole. What I'm showing here in this blue is the curvature of space-time. This is called an embedded diagram. Okay, and there is something similar, also a solution of Einstein's equation that is known as the white hole, that would be like a source of space-time instead of a sink of space-time. It would be like water just coming out, right? And we have the same, except that waves cannot get close. They can just up to here, and then the space-time, the flow is so strong that they cannot get any closer. And if you're thinking, oh wait, this is too complicated, I cannot imagine this, right? So you don't need to. Here's a picture. Our American friends already built it. This is, yeah, okay, they built it. And what we are talking about is waves here. Like here we have waves going all over, everywhere, but here the water flows so fast that waves cannot escape, cannot go out. Basically, this is what we're talking about. And the first one to realize this was Wilhelm Unruh in 1981. She was giving a course on fluid dynamics, and he realized that the equations are the same equations that he used to solve for gravity. So he published it. The waves in a flow have the same kinematics as black holes. And a few years after, he came up with this analogy that I like to use to explain it. So we have three main ingredients to have this analogy. One is a flow of some fluid, of course, with the velocity u, that for now we consider that it's constant, like the river. Then we have some fish that has a maximum velocity, right? You can write it c if you want, but that would be the waves at the end. And then we have a change of flow, like here. Here it's close to a waterfall, and therefore the flow is faster every time, right? And we are supposing that the flow is so fast in a certain distance that the fish could not swim upstream after that. So we have this. Basically, we have these three regions: a slow flow region, this that we call the point of no return, and the fast flow region, right? So if a fish tries to swim upstream, if he's in this slow flow region, he will be able to go, right? Slowly initially, and then faster and faster, because he's moving away and he's going to an even slower flow region. And then this other fish, you see what he did there? Stay there. Because that fish is swimming exactly at the same velocity that the river is pulling it to the other side, so it just stays there. And this other fish, he's already doomed to go to the singularity, faster every time. So this is the same kinematics of light around the event horizon of a black hole. And this is the same thing with the white holes. No? We can also make a white hole angular. They cannot get closer here because the light flow is faster here and then slower. Okay, and also this is like the water image for a white hole. So if you open the sink in your house and you have some flat surface, you can see that initially water is flowing very fast, and then it gets slowed down. And you see this kind of ring. This kind of ring was already, of course, known, but you can see that there's no waves here, because all the waves that are here, when they try to go in, they cannot go in, because the water here is flowing outside so fast. this is also the analog of the horizon there. So this is explained in basically the derivation of Hawking in 1974. It's due to a quantum effect. It's in this approximation that is called semi-classical gravity, where they use a quantum field in a classical solution. The classical solution is the Schwarzschild method that I show you. And basically what happens is that you have two annihilation operators and two set of bases and two vacuum. And basically this is, in the end, using Bogoliubov transformation is a mathematical way of doing it. But basically, I mean, if you have seen the harmonic oscillator, maybe in bachelor or in classes, you remember this, no? This here is the number operator in the in basis, and you measure what is the number operator of the vacuum state, and this is 0. Right? But if you measure the same state, the vacuum in the in inside the horizon, you measure it in the out basis, in a different basis. This doesn't have to be 0. This is actually a thermal distribution that depends on these parameters on the beta, and this is the way of doing a general derivation of Hawking radiation that doesn't depend on the space-time, which we would use. So vacuum is relative, and if you do it for gravity, then you obtain the equation, of course, that Hawking showed, that the black hole will have a temperature, and this temperature will be proportional, inversely proportional to the mass. And and here we have this near formula, if you think about it, because it has quantum constant, thermodynamical constants, and gravitational constants. So it's a nice equation, I think. So how does the analogy work? So I told you how to obtain it. This is the Schwarzschild metric. What we do is we always eliminate the angular part. We just keep a ray. So this only C, T, and R. Right, and this is the same Schwarzschild solution written in these new coordinates. And what we can do is we generalize in two ways. First, we don't have to use a velocity profile. If you see this term here in red, it's a velocity profile that depends on the inverse square root of r. So we say, well, we have to keep that. We can just have a general velocity profile. And the second generalization is that we can have another system that has this metric, even though the origin is not from gravity. It comes from something else. It will come from the flow of the fluid. And then we have this equation, which is this general V, and we obtain that this system will also have some emission of thermal emission with the temperature proportional to this alpha, and this alpha is the derivative of the velocity profile at the point that it's the horizon. And if we apply this formula for this case, then of course we obtain the astrophysical formula. Okay, how do we get these analog systems? So there are several ways. I'm just going to show you the one I mainly work on. It's using ultra short pulses of 8 femtoseconds in photonic crystal fibers. So basically, what we will do is to send a pump soliton. If it's not a soliton, it will form there. It's a soliton, let's say, inside a fiber, and then we send another probe pulse trying to catch it. Yeah. This is the shape of the soliton for the nonlinear Schrödinger equation that appears here. And this is the Kerr effect. This is the guy that came up with the idea, with Lugar. And basically the trick is very nice. It's a theoretician trick, I would say, because if you think about it, you need some fluid that moves faster than the speed of light, or at least at the speed of light in the medium, right? Which is c over 1.5. So what he did is this trick of changing the reference frame. So we have here this frame, the track, and the trees. No? So this is the lab frame, because if we study in the lab, we see the train moving, right? But we also have the train frame, where we will see the tracks moving in the opposite direction, right? So this is the analogy that we will use. One will be the fiber, but the fiber is fixed, and the other one will be where the pump is fixed. So we do this change, and when we do this change, we have then the fiber moving to the left, right? And this is the flow, the first ingredient that we had in the river analog. No? Then the second thing we needed was the fish. This is going to be the probe pulse that is going to be moving in this flow, right? Then the third thing will be something that modifies the velocity of the flow. That's what we need, the curvature of space-time, or the dielectric, something that bends light. And in this case, this bending of light comes from the Kerr effect, the change of the refractive index, because we have some pulse of some certain intensity there, so this changes the refractive index. So this bends light, and we can see an analog to the bending of space-time here, right? And if this bending is enough, then we can get the same horizon as we did in the astrophysical case. So just to be very clear, this probe will make this what we call the stimulated Hawking radiation. It will be not coming from quantum vacuum, because we're sending something there and then we will see the effect. This is what we call the stimulated Hawking radiation. But we can really just not send anything and we will see the vacuum dispersion. Of course, this is much harder to measure. Nobody has seen it in optics. There's someone that claimed to see it in Bose-Einstein condensates like 2 years ago. And so yeah, see this? It comes here, it is stopped by this change of the refractive index. And this is something similar to what happens to fish going in the white hole, you know, that they cannot swim upstream anymore. And in this side we have the black one. So we have two analogs in the same pose, one in front and one in the back. So what we do is we have this photonic crystal fiber, similar to what Carlos just showed. This is the same picture. This is the measurements of the dispersion relation. It's always very hard to get the dispersion relation. We just measured here, we did some fitting, and we obtained the dispersion relation. These points here are what we call the zero dispersion wavelengths. They're very useful to see, to relate the images, because we have several dispersion, different functions that we all call dispersion. So these are, inside here is what is called the anomalous group velocity dispersion. So basically what it means is that the group index, instead of going down with the wavelength, it goes up. And this is anomalous, usually it goes down. So this is the second derivative, beta 2. And this is the anomalous region, that is negative. These are the plots that Carlos just showed for several fibers. And we also have our own dispersion, that is the co-moving dispersion, or the co-moving frequency, this omega prime. This is the Doppler effect, basically, applied to the co-moving frequency. And I'm also putting here the omega prime. This u will be the velocity of the pump. Remember, the velocity of our reference frame that we change to follow the pump. This is the region of the zero dispersion wavelength, and between these two lines is the anomalous group velocity expression. The solid line has to be in the anomalous group velocity expression. So we're going to study the negative frequencies, what causes when you include negative frequencies for a single pulse. This is still not Hawking radiation, but it's related because you need negative frequencies, and it was actually proposed after or using the framework of analog Hawking radiation, and this was measured in 2012 by Dept. So what he does is he applied the same theory, but he doesn't have two pulses, he just has the pump. So if you have the pump, you have the same kind of effect, except that it's not Hawking, it's just you have some conservation. Basically this conservation of frequency is a way, it's a simpler way of looking at the phase matching conditions. So instead of conservation of momentum, you have conservation of co-moving frequency. You change that to this, and then it's easier to see because you just put a straight line and you have all the matching conditions. These two were already known. They are the Cherenkov radiation or the resonant radiation. But as you see, with this very suggestive image, is that you have one more matching, right? Which is, it seems weird because it seems to be a combination of positive and negative frequencies. So what is negative frequency? Why do I have this match? It seems like I can only apply the theory here or here, no? And they're supposed to be the same. And they are. But can I apply it also to these other quadrants, to the second and fourth? And so basically people were not sure, but he did it, he measured it, so we can. So what I'm going to do now is to take the absolute value here to put this point here on top. But I put these dashes to remember that they actually have negative frequency. And basically you have this then another point, and this is what people call the negative resonant radiation. This is a figure from the paper where they see the peak here. They see exactly here where this is the negative matching. This square will be like this square that they are showing, and just reflecting the negative resonant radiation. So they measure it, and we have negative frequency radiation. So what we're doing, we're following this paper of how to explain this. We're using the electric field and analytic signal. There are two frameworks that you can use to explain this. They are related. Basically, what the analytic signal, I don't know if you can see here, basically cuts. It just takes the positive frequency part of the electric field, right? And it's not going to be real anymore. It's going to be complex. So then, in this way, the electric field like takes these 4 points, and the analytic signal takes this also 4 points, but in a different way, right? But in this way, you can make it explicit. This is the nonlinear Schrodinger equation that has the dispersion and the nonlinearity. Here, it's what is called the unidirectional pulse propagation equation, that is more general because it includes a full dispersion instead of just one term of the Taylor expansion. And dispersion in the nonlinear term that is not present here, this is a constant, and it has a full clear ordered nonlinearity. So what we do is then we write that equation with the analytic signal, then we divide basically the electric field in positive and negative frequencies, and what we have is a separation of terms. Yeah? We have these terms that one of them gives me the new phase matching condition, that this was not known before. But this was explained with this analytic signal. So basically this is what we want to do. But now we're going to study the two pulses. We go back to the two pulses. What we have, as I told you, is not the vacuum that is stimulating. It's actually, we send some excited state, which is this probe pump. And then the Hawking radiation is amplified. It's supposed to be the same frequency. Well, it is the same frequency, just amplified. Right? So this is the same thing that I show you. It comes, and then it will get reflected, it will get shifted, and it will have a new emission. So you'll have these two emissions, one in the infrared and one in the UV. Right? I can do the same thing on the other side to probe the black hole. We did both things in the experiment. And so this is, if you see this dispersion relation, I'm putting it again. If you take the derivative of this and equal to 0, then you have that those poles will feel that their velocity is equal to u. Of course, this is the velocity because we define it like that. That is the velocity of the solution. These two are mathematical points. There's nothing going on there, but there are frequencies that will have the same velocity as the solid. So if we send a probe close to there, this is what we will know in the horizon. What will happen is it will get shifted to these other two. They are predicted by this conservation of omega prime. So we will have these two extra signals, let's say. This theory predicts that it will be two extra signals that are the positive and negative analogs of Hawking radiation. But besides, we also have all these other signals just from the pump. So we use the same framework to analyze the analytic signal. It's of course more complicated because we have one and two at the same time. But we have extra terms, which is this cross-phase modulation conjugated. This is a good extra term that will explain Hawking radiations. Basically what we do here is use the usual method to get the new generated frequencies from a nonlinear interaction when there are two pulses. But we apply it to the equation with the analytic signal. And then what we get is basically this new phase matching condition that describes positive and negative Hawking radiation. This is like usually what we put to show that the lab frequency is conserved. And this is what you would usually see if there's a momentum conservation, but we change it to co-moving frequency. Co-moving has a front here. Then it's easier to see that they're equivalent. And when we do that, we realize that there are some extra connections. This term, this is the positive Hawking radiation, the blue term. This green will have one negative Hawking radiation, and this is another negative Hawking radiation. But if you do the conservation of energy, you see that there are underlying connections that nobody has seen before or more. That there are between these colored terms, let's say. There's this relation. And those are the only ones that can conserve energy because they are phase matched. Okay? So what we did is just apply numerical solutions to basically to check with the experiment that we did. This is so we have everything to match the same experiment and we have the same things, but we just wanted to do exactly the same. This is how if you see this input light, then you can see the extra signal. This extra signal was not seen if you don't use the analytic signal formalism. You just see this frequency shift. And well, it matches the predictions. Yeah. So this is the initial field, this is the probe signal, the pump signal, and we have some other things, let's say, after of the numerics. All these other numerics, they are explained by the phase matching conditions that we obtain from all the terms. In particular, there is a negative resonant radiation that matches exactly where it is. This is the red signal, if you want, the red signal. And we also have the same for the positive Hawking radiation and for the four-wave exit. Right? And the errors are very small, but this was expected. This is the experiment just to compare, but the comparative is the same. We already have the same, the agreement, a very good agreement with the experiment. This is the measurement of the negative Hawking variation and the positive of Hawking variation produced by the white hole and by the black hole. So this is my summary. Basically, we can now explain using the analytic signal formalism and the theory, the usual theory for the phase matching condition. We obtain these new phase matching conditions for the negative Hawking variation that agrees with the numerical solutions and with the experiment that I did not talk about, but that we also did in the stimulated case. And these are good pictures of Cinvestav in Mexico. Thank you.
We have time for 2 or 3 questions. Questions.
Does the negative frequency formalism have anything to do with rotating wave approximation? Is there any relationship, or is this something completely different?
It's something completely different. It's basically what we're using as a basis for our pulses. So when we use the exponential basis, we always really have both of them. Right? We have positive and negative because it needs to be real. And we somehow decided that positive is enough, and it's usually enough, except when you are in these extreme cases where you can have the positive and negative frequency.
Yeah, I guess the way I often think of it is we start off with the idea that the frequency is positive. We use the exponential notation, which when you have both terms is just a standard sine omega t, and then you write it in the exponential term, and you have both terms. If you want the thing to be a real field, you would have to have both terms. And I'm having a hard time formulating my question. So tell me, what question should I be asking?
Well, what I can tell you is that it is actually explained by both formalisms. So both formalism agree, but you just need to do it right. If you do it with the electric field formalism, you just need to keep positive and negative. And then you will just have less terms, but you will see the same signal. I did it. It just takes a bit longer because it's not the most efficient numerical function to solve, to propagate. But you can also do it. Just take a bit longer. They agree exactly. They are exactly the same. But we have an extra flexibility if we use the analytic signal formalism. That is that the terms, instead of dividing in just 4, they divide in 16. So we can turn on and off each term and then realize which is the actual origin of the negative multiplication.
Another question? Thank you, that was really interesting. So you can make light at about 200 nanometers? Is that the right one?
230, yeah, 231 nanometers. And the other one is in 1550. Yeah.
So fiber optics is pretty low loss, but it's not completely low loss. And particularly probably when you start to get to 240 nanometers or so. Is loss a problem in the fiber? And is there some, you have these nice pictures where you only talked about the refractive index, but there's of course the loss, which would be the imaginary part. Is there some analogy with that in the Hawking variation?
So this is the two-part question. The loss in the propagation is not that important because there's only 7 millimeters. So we have the loss in the propagation is negligible. We just have the coupling loss. But the loss in the UV part is very important. So the first experiment in 2008, they measured the infrared part with an efficiency of 10 to the minus 6. So they tried to see the UV part, and they couldn't. Right? Now, this is like a proved experiment in 2019, we just published, that the infrared part basically has the same, more than 10% of efficiency, the infrared part. And with that, we were barely able to see the UV part. And actually, the simulations, they agree with the frequency and the measurement in the experiment, but they don't agree in the amount. So the simulation, they show that it's 100, it should be 100 times stronger. So of course, we believe that because the losses are higher there in the UV part, it's closer to a resonance of the silica too, which is in 190, I think. And also it's very multiple there. So our simulations, they are approximated that it's only one single mode. So we're losing in another.
Yeah, could you envision if you could solve this loss problem of using this as a way of making UV light? I mean, it's kind of a four-wave mixing process, and so people like four-wave mixing for making light in many different colors. I mean, is that something that you could envision it being a source of?
I mean, but this is nothing to do with the four-wave mixing. It has to do with the fact that the only way to do it, I think, is to change material. But then you need a material that you can engineer the dispersion relation. You have, basically, this is what we chose. We have like 20 photonic crystal fiber, and we chose the one that have the photons at frequencies that we can measure, that we have the detectors and the board. So a way to do it would be to change the frequency, to change the fiber, to move the frequency, or to use a different material that doesn't have that one. Maybe a wave guide, for example, made of some material that has a high nonlinear tangent also.
Okay, we think the